Hey, welcome to my series on deep reinforcement learning on Halite 3. In this video series, I want to give a brief introduction on what I already did on paper so far, and then I want to implement deep reinforcement learning, which will learn to play the game of Halite 3. Just as a short introduction, this is not really meant as a guided video. It's more like I will just record myself while I code it, so it will be full of errors and bug hunting and whatnot. But I think it may be valuable to some people. Okay, what have I done so far? I wrote a small tutorial on how deep reinforcement learning for Halite 3 could be set up, although I have not reached the point of deep reinforcement learning yet. Brief introduction to Halite. Halite is a game of 2 or 4 players on a map. Each player can build and control ships that can collect the resource, and you can use this resource to build more ships or build more bases or something like this. And in the end, the player who has the most Halite in the bank will win. What do we see here? Here's 2 players. It's the green player and the red player, and you can see that these little turtles are the ships, and the ships are moving towards these bright spots, which indicate how much resources on each of these fields, and try to collect it and bring it back to the base. Over here you see some statistics on the players. You can see that when the ships return something, the amount of Halite in the bank goes up. And here you can see a graph over charting the resource content of the bank of the player over the game. One thing you can note over here is that a typical strategy back when this competition was active was to basically spend all your Halite up until the middle of the game, or maybe the last quarter of the game, and then just start collecting with however many ships you manage to build on until then. Yeah, I mean, there's a whole bunch of rules, like when you move around, the ship always has to pay some fuel costs depending on how much resource are there. You collect a certain amount of resource, blah blah. I think you can read this if you want. What I did initially in this tutorial is I started with Q-learning. Some people might think this is funny because this is not really a good task for Q-learning. I agree. The way I originally went about it is I just implemented neural networks, like according to some tutorials and whatnot, and then found that stuff's not working. When I started reducing the complexity of the problem, it still wasn't working, and then I just thought, maybe I can try to find a really dumbed down solution using the Q-learning algorithm. And while doing this, I found that I had a whole couple of issues with my code, and that's why it was not working. So I started with this first. And also this helps to introduce some of the more difficult things. What's difficult when you do reinforcement learning that is not in a gym environment? Some people might know the OpenAI gym, which is I think what most tutorials, let's load some of the tutorials I've also listed as references, do. So this breakouts game, for example, is used in the OpenAI gym. What does the gym do? It wraps this game behind a nice interface where you just say, oh, I want to do one step in the game, and then it returns to you already what's the state, what's the reward, and so on and so forth. While if you do stuff by yourself, you have to come up with how to represent this yourself, and I found this is not necessarily easy. So how would we go about representing a game like this, the state? Initially, in order to just get a network which learns something and not a network which is perfect at playing the game, I want to model whether my network can learn how to collect resources, regardless of how much you have on the bank and whether you win and building stuff. I just want a network which is good at moving the ships around and collecting resource. And in order to model this, I thought a good representation to start with could be 6 2x2 feature maps, which is the amount of resources on the given field and whether there's a ship. One is for my own, -1 is for my enemies, for the enemies. The amount of resource that's carried by each ship, whether there's a structure, 1 for owned, -1 for enemy, and then one hot encoded matrix of the ship that is currently trying to make a move. This is kind of a mix of these two tutorials. So Joshua Staker, who was one of the best machine learning bots in Halite 3, has very similar features. You can read his tutorial, it's pretty good. What I'm looking for is this one. He has a very similar feature map. You have the main game, you represent the resource somehow, then you have the ships, then you have how much the ship's loaded, you have the bases, and so on and so forth. So you might also notice that I wrote 6 features here and it's only 5. That's because in the last edit I actually changed this to not have separate feature layers for owned and enemy ships, which initially I had these in separate layers, and also for the buildings. Here's some code. Here's my less nice graphics of this, and then you can read all of this if this is interesting to you. Another interesting part is actually how do you model the reward. In the OpenAI gym, it will always return you what's the current state, what's the reward, is the game done or not, and in this game you need to come up with it by yourself. There's probably multiple things you could think of, which is, okay, the reward is however much. You could try to tie the reward to the global game Halite amount on your bank. So for example, in each step you could say whatever this number is would be my reward for this step or something. I will try to model the reward as something that is ship specific. So for example, if I have a ship which is next to the shipyard, which is loaded somehow and it moves on to the shipyard, then the reward would be whatever the ship just deposited onto my account. And then you could say, how do you model the reward for moving around? Initially, I'm going to leave this as -1, so no matter where the ship travels, it will always have a -1 reward, except if it drops off some resource, and I will hope that it learns to drop off more resource by playing many games. But you may also think, okay, maybe moving around, the reward is actually the fuel cost of the ship, and I don't know, standing on a cell is the reward is to the resource that the ship actually loads into its container. While playing with this initially, I found that your ship will, for example, learn to just stand still somewhere. So if moving around has -1 or fuel cost as reward, the ship would just stand in the shipyard, because standing there is no resource cost at all. If you give a positive reward for collecting resource on a field, then it will also just stand on the field and just stay there forever, because it's a positive reward. So then somehow your reward function would need to change over time, which is something we can try later. But I actually found, after I found the bugs in my code, that a reward of -1 works. So sorry for the fast moving around, making a move. Where's this reward section? Training model reward. Yeah. So bringing the resource to a base is a positive reward. If the ship is crashing with another ship, it's -1000, because we lose a ship and the ship costs 1000. And anything else is a reward of -1. So we're gonna leave this. We implemented some Q tables. Q tables are not really suited. Q learning is not suited for this task, because it's really hard to find a representation for the board that generalizes. If you use a representation like this, for example, then as soon as the board has a slight change in resource on any of those fields, it's a different state and you have no idea what you should do. So you need almost infinitely many games to learn anything meaningful. So back when I trained this when I built this queue table, I kind of cut down the game to a point where actually it was only my ship moving, so that the opponent does not change the playfield too much, and I rounded the values of halite on each field to some number, so that I can somehow find a discrete representation of this that has less distinct states. So I don't know if there's like 1,000 resource on this field or 900 is probably not so interesting, versus it's 1,000 or just a 10 resource, like maybe here or something. So I don't know, as as general as you can make it somehow. So I did this with one ship, and then also if you think in number of turns, like the number of ways that you can move around randomly within like the first 50 moves or something is already so huge that it will take almost forever to learn anything meaningful. So I only trained it for whatever 10. I said maybe the Q learning algorithm can take the first 10 moves and find the best combination of moves. I actually represented these feature arrays as a hash to put it in my table, and then you have like the hash, the move that was taken, the reward, whether it's a terminal state or not, and then what's the current queue values for this particular state. So this is when the table is uninitialized or after the first game. The last number in this array actually represents how often we have seen this state. You can see here I ran it for a couple more a second time, and then down here I ran it for 500-ish iterations. Here you can already see that it found one move combination which leads to some reward. As soon as the ship drops off a reward, while the game might not be finished, I consider this to be a done episode for the ship. We found this already 8 times, and it kind of learned that this is the way to go. Is there anything? Yeah, down here I tried running it for 20,000 episodes to see what can I find. It actually also found the best possible move combination in the first 10 moves, which, if you look at this GIF, is start in the middle and move to this big blob, collect as much as you can, and bring it back. Yeah, so, but this is not super impressive, right? You could have just coded this by doing some breadth first search, or just, I don't know, randomly move to the first biggest spot that's close to you and collect it. So we will see this much more interesting when we start using neural networks, because a neural network will generalize over this. So a neural network will learn that if there's like 1,000 resource or 950 resource or 800 resource, this is kind of the same thing, and it will just move here and do this. Also for a neural network, while initially we will probably just train it with one ship to see if we can reproduce what we have here and kind of make sure that we didn't introduce any bugs or errors into our code, we will then quite quickly, I want to move to building multiple ships. Let's say we train it so that it will build up to 5 ships or something. And then also longer episodes, not only 11, but let's run it the full 400 moves or something like this. And then, we will see how far we can go. Overall, for this network to get good, I will take some inspiration from what Joshua Staker did here. He has some network which is fairly deep. I think we will not go that crazy, but he actually added some features which are about the map, and some meta features like how much of the global halite is still available and so on and so forth, and then also some more features around the opponents. And his network actually predicts A, the moves, and B, whether it should build a ship or not. So this is something that we will explore all the way at the end. I started the chapter about deep Q learning here. Here's some introduction. I will also start linking most of these Medium posts, which are definitely read-worthy. Like that's where I got all my information from. Sorry, I'm clicking too fast, I guess. Another thing we will do, and probably I will make this separate video, so this is going to be the introduction. We will just copy the network that beats Atari. So basically I will check, I kind of forgot which of the posts was it, but yeah, I think this is from the DeepMind Atari paper. You have some convolutional layers and so on and so forth. I will copy this network, even though in my initial experiments I just used my own network. Yeah, this is kind of the structure. We will see. If I feel or find that it doesn't work by just copying this Atari network, I will go back to what I did previously and yeah. Okay. So for the first episode, I think this is it. In the next episode, we're actually gonna get our hands dirty.